Hello, I'm Nilay Sheth, one of the team members of the wristwatch multimeter. So what we've done is we've finally managed to get this prototype in our hand, and it is currently ready to take readings from probes from the external world and display it directly on the LCD. And it has a very nice graphic user interface, and it can be linked to computers. It can be linked to. We have a Bluetooth module sitting right behind the LCD, which sends data directly to your Android phone or to your laptop. So that is what we've been able to do. We've been able to replace all the bulky devices that we had to carry around, such as the big multimeter, big knobbed multimeters, which had ranges with complex ranges and etc., where you had to know what range of the reading are you supposed to be measuring, and you had to set knobs for that. You had to carry complex oscilloscopes just to measure readings with your device. So we've been able to compress the entire module of the measuring instrument into a small wristwatch size product. So what we'll be doing now is we'll be opening up the product so that we can show you all the modules that have been used in the project. This is the Nokia 5. I'll just remove the power for a sec. This is the Nokia 5110 LCD module, which was easy to interface and gave us the precise readings directly on the LCD. This is the Bluetooth module, which was sending data directly to the laptops and to the Android phones, so that we could plot data easily. These are all the user inputs. This is for scrolling. This is just a potentiometer coupled to a ADC for scrolling, and this is just a GPIO button that we've connected to. So basically this was a shield, and I'm just opening the brain of the entire multimeter that has been used here. Regarding these ICs, this IC is the main op-amp that has been used for scaling all the voltages down to the levels which we needed it. This IC is the optocoupler, which isolates the op-amps and all the external circuits that have been scaling down the voltages to the microcontroller, so that the microcontroller doesn't end up giving excess currents or taking excess currents to blow itself up. This is the buzzer that has been used in the continuity test that we generally do between two short points. This is just wires connecting the two modules. So the IC which has been set in here is the analog switch IC, which Keval earlier described here. It works as a knob, sending different voltages as a ADC, and we don't have to worry about ranging since we have incorporated auto ranging in our code. Auto ranging is a feature where the device smartly comes to know that the reading isn't within the range of the working of it's not getting the correct reading for the quantity it's measuring. It's either getting a 0 or it's either getting a full scale, so it changes to the next range possible. We'll be using the product to test out a few resistances here. It is showing the normal time as a normal wristwatch does. We'll be going through a menu now where we can choose various modes to whatever we want to select. And we have a potentiometer here which will be used for changing the options in the menu. So I'll set it to the ohm meter option, and we'll be checking out a resistance right now. So here we go. I go to the ohm meter menu and I pick out a resistance randomly from the resistors, and here we go. So we have the resistor already displayed. It's showing 1.2 kilo ohm, and as the color code says, it's exactly a 1 kilo ohm resistor. I again go to the menu and select DC voltage, and I hold it against the battery, and here are the voltages. So it's showing me a 12.23 volt on the battery, and it's showing that the process is complete. Coming back to the normal menu, we'll be testing out continuity now, which is directly a feature in our multimeter. As you can see, we can directly try it out on a wire, and I'll directly show that it gives a strong beep that it's a continuous line. Against a resistor, it shows nothing, so the continuity feature. So as you can see, we are on the main menu. We'll be testing the AC voltmeter now. So I go to the feature and I connect the probes inside, and there you can see that the reading is already there. So the AC voltmeter of our Switchtorch multimeter.
Here the block diagram of our project. The block diagram mainly comprises of two parts. The upper one works as a multimeter and the lower one works as a function generator. In multimeter we are using analog switches instead of using knob to measure the thing what we are going to measure. These analog switches are works according to the instruction given by the microcontroller unit. The output of these analog switches are given to four parts: DC voltmeter, AC voltmeter, ohmmeter, and the fourth one is used for testing purpose, that is the connectivity. The output of these parts are given to microcontroller which drives the output. This output can directly seen on LCD screen or on our laptop or mobile using Bluetooth or using a communication protocol like SPI and I2C. Whereas the function generator, we have designed to produce four types of signals: sinusoidal, square, sawtooth, and triangular.
After seeing the block diagram, let us see the design of our circuit. This is the EagleCAD model of our circuit. It consists of the main brain MSP430 F5529 microcontroller, designed and manufactured by Texas Instruments. The four modules are AC voltmeter, ohm meter, DC voltmeter, and the function generator. These four modules are created using LMP7704 op-amp, designed and manufactured by TI. The output of these four modules along with the input signal is given to the analog switch TS5N214, same designed and manufactured by TI. The output of this analog switches drives the optocoupler ISO7221. The output of this optocoupler is given to the microcontroller ADC channels. This combination creates an isolation between the input and the output. The output of the microcontroller is given to the LCD screen via Bluetooth.